Okay. So we're talking about it. Right, we talked in the last video pretty much about how, position is relative, right? And I'm going to actually write it down real fast just so you guys have an inkling of what the mathematical transformation looks like. It's pretty simple, actually, right? So the guy on Pluto, he's in a different coordinate system than us, as I would part it, or as physicists would call it, a different reference frame. And in his frame, he has coordinates we'll call x prime. And these primed coordinates, so to speak, well, they measure us like this, right? Where we have some constant velocity between us, right? Because Pluto's just moving at the same speed. Earth's just moving at the same speed. There's a relative velocity between us, right? And so because there's a relative velocity between us, our position's also relative, right? All velocity or speed, quote unquote, is just a change in your position over time, right? It's not that big of a deal. And so what we saw in the last video, that the principle of Galileo, the Galilean relativity, was that this concept, position's relative. it's not that big of a deal. But I did ask you a question, didn't I? And I did ask you to ponder it, right? And that question simply was the fact that, or the statement. Does it make sense to talk about different positions, but at the same time? And before I answer that, because I'm going to answer it for you, there is a definite answer. You may not like it. There is a physical, experimentally verified, because we don't prove stuff in science. That's for the mathematicians, which we'll talk about in this video. We don't prove stuff in science. I just really want you guys to understand that. We verify statements. We don't prove stuff, though. We say, yes, given that logic, I can show you that under those circumstances, it's true. So keep that in mind. Under those circumstances, it's true. And I verified your statement, but I will never claim something is true, right? I will never say prove something. That's for the logic. That's for logic. Science, I can verify something. So the statements that we will show later on the video have been verified experimentally. But let's go down a little history lane. So in the 1800s, we went through something which I would call the electromagnetic revolution. And in this revolution, we figured out the mathematical relationships between these charged objects and the electric fields and the magnetic fields and all that good stuff. And there's a concept in physics that in the modern world we call invariance. And it goes back to this concept. Physical laws really shouldn't matter who's looking at them, right? If I say, for example, that the electric field operates, and this is just mathematical jargon, you guys will probably, the people watching this video may never understand what it means, so it doesn't matter. Shouldn't care, right? And all this is saying is that the divergence of your electric field depends on your charge density over this constant. Okay. But it shouldn't matter on Pluto, right? This is a physical law. And so the laws of physics must be invariant. That's something we strive to say. And guess what? The rules of the electromagnetic fields weren't transforming correctly under this guy. Yikes. But they were able to transform them. Actually, it's those mathematicians that were able to prove things. The mathematicians proved how to transform these laws, by the way. It's not just this one. There's 4 sets of electromagnetic rules in the modern world, or if you do differential forms, there's 2. And they figured it out. So these 2 mathematicians, they were able to prove how the electromagnetic fields transform to make them invariant. And they're actually very similar. I'll write down the first, the positional change. The positional change transformed under this. You might have a little sigh of relief. You're like, I don't know what that gamma is. But hey, that's the relative motion thing you brought up earlier, Ramin, right? I know that. It's like, yeah, that is. Good job. And you know what? I'm such a nice guy, I don't even tell you what that gamma is. It's just a number, right? It's just a factor. But these mathematicians, they proved something else. They proved something else, that the electromagnetic fields, in order to be invariant, right? These are true physical laws that other observers actually measure time differently, and they couldn't accept that. But they showed it mathematically, right? Because at the end of the day, they just care about the mathematical relationships, right? And so this is 1904. So we went through the electromagnetic revolution. We found our Maxwell's equations, how our divergence of electric field we saw. There's a divergence of the magnetic field, it's 0. There's the curl of the electric field, or as we say it, if you change your electric field, you have a change in your magnetic field. And if you change your magnetic field, there's a change in your electric field. Those are just Maxwell's equations. And what they figured out is in order for them to be invariant, hello, gamma again. Uh-oh. And these right here are actually known, something special in physics, because of the mathematicians who proved that's how the electromagnetic fields were changed in order to stay invariant, which is just, once again, the concept that physical laws shouldn't matter who's looking at them. If they're a physical law, they're a universal law, then it should be the same, which makes sense. And so we call these Lorentz transformations. But the mathematicians couldn't figure it out, right? They didn't know what this bad boy meant physically. Time is relative? That can't be. So they wanted to reject electromagnetism. But it wasn't until 1905 that a man called Albert Einstein came up with a paper. He wrote a paper, and I believe the title of the paper was called On the Electrodynamics of Moving Bodies, right? It makes sense because we're talking about relative motion. The guy on Pluto moves relative to Earth, and he solved the puzzle. He said, two observers with identical clocks that move relative to each other will observe time differently. It still blows my mind every single time I say that statement. So I'm going to say it again. Two observers, i.e. me and some guy on Pluto, our clocks will physically measure time differently. And the relationship between the time between our two clocks is calculated by this. Lorentz couldn't figure it out, Poincare couldn't figure it out, but our boy Albert Einstein was. Point for physicists. And I just want you guys to understand that. That is not, it's not a thing about, perspective. It's not a definition. This is a physical fact that has been proven over and over and over, and you can actually do it yourself, right? Take two, you probably have to have a little bit, I don't think you could do like a kitchen timer, for example. example. You need a more accurate clock, but you can do it, right? Start 2 clocks in your room. Take one, leave one in your room, take one and go on an airplane, right? Because now we're doing relative motion, right? We're doing relative motion. And you can figure it out mathematically, because for this one, you're not going to be able to calculate it with this one. This is for constant velocity, right? If you have variable velocity, you actually have to do an integral. It's still not too hard. Yeah, I could probably give the video, the formula in the next video. I'd have to calculate. I don't know off the top of my head. But if you have a variable velocity, you can calculate it. So you can prove it yourself. Take your phone, maybe your phone can do it. Anyways, take 2 clocks, leave one in your room, take one and go on an airplane. Right? We started them at the same time. Go wherever you want. Come back. Your clocks will have measured time differently. You'll say the time between the 2 events are different. Isn't that wild? But it really isn't. Time is just relative. So, it makes no sense. Just like to say there's no absolute position, there's no absolute time. It makes no sense, guys. It makes literally 0 sense to say these 2 things happen at different places, but at the same time. Time is relative. You have to be specific. Just like with our relative position, you have to specify. And in the next video, we'll actually talk about it a little bit more. This kind of the philosophy of why this has occurred. And actually, as there was a guy called Newton. Newton kind of introduced this concept of an ether in order to make his laws make sense. And kind of messed it up, in my opinion. You know, people love Newton. Einstein even apologized to Newton in this paper where he figured out the physical meaning of this. So, what did we conclude? What is our modern understanding of space and time? Well, our modern understanding of space and time is that your position is relative to the thing you're talking about. But not only is your position relative to the thing you're talking about, how you measure time is relative to the thing you're talking about. 2 identical clocks that move relative to each other will measure time differently. This is a physical fact. And so in the next video, we will talk about kind of how did we get here? Why is this such an interesting concept? And it's not because these concepts are so wacky, it's because they've been ingrained in us, right? If you think about it, all this really is saying is that, you know, you have to just be very specific on what you're talking about. But I will conclude the video by repeating the concept once again, the physical fact once again. Time is relative. 2 clocks, 2 identical clocks that move relative to each other will measure time differently. Once again, you can do this yourself. Take 2 clocks that can measure time accurately, start them at the same time in your room, take one on an airplane, come on back. They will have measured time differently. The one on the airplane will have measured, I think, time a little bit faster than the one left in your room. And it gets even wonkier, guys. And maybe like 3 videos from now, we'll talk about, does gravity have a role in this? We've been talking all about this acceleration and position. Sorry, we've been talking about all this stuff about velocity and position, but does acceleration play a role? And to conclude, I'll ask you that question, right? Position is where you exist. Velocity is your change in position. Acceleration is your change in velocity. Does that matter? And I'll leave you guys with a thing. For the mathematicians out there, right? This VT is a constant. I want you to ask yourself, what is A prime? That will be the key to the video. Just take the derivative twice. Just take the derivative of this twice with respect to time. Oops, sorry, I shouldn't use C here. I'll use K for constant. Hint. Derivative of a constant, 0.